Okay, so what we have done so far, now we know that how can we evaluate the line integral if you are given the integrand in a scalar field. Okay, so you have to convert ds into dt using the formula of speed. Okay, if you want to solve in the line integral in terms of t. Okay, so before I proceed to another thing in line integral, so just look at in your notes on the first page, I think. So you can see here, this is the length. Okay, if you are given a curve, so we can also evaluate the length of the length of that curve, or the length of the arc length. Okay, if you know the vector function or the parametric equation of that particular curve, where the formula is the integration of 1 ds. So there is 1 here. Okay, so if you have the integral, which means that there is function in to be your integrand, whether in terms of xy or in terms of xyz ds. So this is about the mass. Okay, we can evaluate the mass of the very thin rope. Okay, the mass of the worm munching the soil and so on, munching the soil along the curve C, But if your integrand is equal to 1, so you only have 1 ds or just ds. So we know that ds here is the arc length, which is the length of that curve. So this is reduced to be finding the length of the curve. So then what is ds? So we use the same formula, which is convert into dt, where you have to apply the formula of the speed. R prime, magnitude of R prime, which is the speed, and you have dt. So now you have to find out the t from t0 to t equal to t1. Okay, for example, actually this one you have learned, I think if I'm not mistaken, you have learned this in Math Method 1. There is a topic of arc length, the revolution. I don't remember exactly the topic, but you have seen this before. Okay, but now we just recall this. Okay, so let's say you are given a curve. So your curve is represented by the parametric equation, where you have x equal to minus 2t plus 1, and then your y is given by minus 4t plus 2, and z equal to 4t minus 3. Okay, so then the t is given, the limit of t is given from 0 to 1. So now we want to evaluate the length of the curve given by this parametric equation, which means that you can form the vector function, where the parametric equation here tells you the function for each component x, y, and z. You have negative 2t plus 1, minus 4t plus 2, 4t minus 3. Okay, before we proceed, maybe you want to know what is the shape of this curve. Do you know that? And as you can see here, all the function here, they are all linear equation. So since it is linear equation, so of course your curve here is a straight line. Okay, so this is a straight line. Right, so now we want to get the speed. So based on the formula here, you have to find the speed. So r prime t, and we have minus 2, minus 4, and 4. And then find its magnitude. So the square root of 4 plus 16 plus 16. So this will give you 32 plus 4, it give you square root 36, and you will get 6 here. Okay, so now when you replace here, we want to get the length. Okay, the length of the curve. So you have the speed is 6 dt, and t is from 0 to 1. So 6t 0 to 1, so you will get 6. So now you know the length of the curve provided by this parametric equation is 6 unit. Okay, just 6. So this is I would say that this is not the topic that we want to learn, because the in the course information, so the aim is to know how to evaluate the line integral. So this one is maybe just part of your understanding. How can you relate the curve and the line integral? Okay, because the thing that we want to focus is we want to evaluate this one. So the length of the curve is part of your understanding, where you have learned that before. Okay, all right. So next, we have done this one, right? We have done this, the additivity. Okay, so we're done for evaluating the line integral for scalar function, where your integrand is a scalar function. Okay, so now we want to look how can we evaluate the line integral if you are given a vector field. Okay, like, for example, let's see, now we look at the type of question that you will be asked. Okay, you are given a vector field f, and then evaluate f dot dr along the C, where C is the curve defined parametrically by all these parametric equation. Okay, so can you see this one? So this one is the line integral in vector field. If you are given, you must be given the vector field, otherwise you cannot solve. So in the question, in the instruction, they must provide you the vector field. Okay, general form of the line integral for vector field if is given by f dot dr along the curve C. So that is the general form of the line integral for vector field. Compared with the thing that we have discussed before this, you have the line integral as well, but your function is in scalar form. So you have just f, small f, and you have ds, or maybe you have dx, or maybe you just have dy, or maybe you just have dz, where for this you need to transform into the dt. So that is the thing that we have learned before this. So now we want to focus on the how can we evaluate the line integral if the vector field is given. Okay, so that is the question looks like, where you must have the information about the curve as well, otherwise you cannot solve. Okay, so now we look at the general form of the line integral of the vector field f along the C, along the curve C. So let's say your C is an ellipse, so you can see the ellipse here. So the ellipse here. So the line integral along the ellipse. Okay, if your ellipse is in 3D, so this is your ellipse looks like. Okay, so the idea is the same as we have looked at before this. We are computing the mass. Okay, the mass along this a line, a thin rope or wire. So you want to compute the mass that you are passing through inside the very thin wire. Or assume that there is a worm inside this tube. So the worm munching the soil, and you can evaluate the mass of the soil along this ellipse curve. Okay, and this one is in a more general curve. So that is the line integral for vector field. Okay, So the vector field is just around the curve. Okay. Okay, so let the vector field F be a vector field and C is the curve, and the curve is given by in a parametric form or in a vector function. So the line integral of the vector field F along or over the curve C is given by, actually, if we relate this, so we have this one from scalar field, right? You have the ds, and then how can you have the scalar field from the vector field? So in this case, we have to get the dot product between the F given and the tangent vector of the curve. Okay, the tangent vector of the curve. So T here is the tangent vector of the curve C. Okay, so when you apply the dot product, so you will have the scalar function ds, where it reduced to line integral that you have learned before. Okay, but this one will take some steps. Okay, some steps. So instead of we do it one by one, instead of we first we differentiate the r, you get the r prime, and then we need to transform the ds. So we can simplify that using this one, where we know that the tangent vector is dr over dt. Okay, and we know that ds is the speed, right? The magnitude of the r prime. So instead of you have to do the r prime again and again. So we can simplify the form to be just f dot dr, where f is given, dr is you have to find the derivatives of the r. Okay, so I will show you later how can we evaluate this. But in general, this is the most general one. But after sometimes when we replace this in terms of dt, so now it reduced to f dot dr. So now you have to bear in mind, if you can see the question which is related to f dot dr, there is first integration of the f dot dr. So we understood that this one is the line integral for vector field. Okay, so in this case, we don't evaluate the line integral using this. We don't evaluate using this, but we evaluate the line integral for vector field using this one. Maybe you want to know how can we convert from f dot t ds to this one, and then after that we can have this. Okay, maybe I can show you here. So we know that the t is a unit tangent, right? We have learned that one, where you have the r prime over the magnitude of r prime, right? Okay, so now f. Now we want to I want to show you from the TDS, how can we have only dr? Okay, I want to show you. Okay, how can from TDS we can have dr dt, and after that we can have only dr. So t, we know that it is a unit tangent vector, so r prime over its magnitude, which is the speed. Okay, and then ds, what is the formula of ds? So ds is, we know that it is r prime, and also its magnitude dt. So when you put them together, TDS, so TDS is r prime t over its magnitude, and ds is r prime t dt. So we can have this, where you have dr over dt. So now we have a dt and you have a dt, can be cancelled out. So that's why t dot ds becomes t ds is become only dr. So that's why you can only have dr here. Okay. Okay, for the vector line integral, if you have a scalar field, we can compute the here we can represent the mass, or we can represent the mass. Okay, we are evaluating the mass along the curve. Okay, but if you are given a vector field f, or you have f dot dr itself, you have f dot dr, and if your vector field here is a force field, so then we can say that the f dot dr is the work done. Okay, the work that you have done based on the force field that you have. Okay, so meaning that the physical interpretation of f dot dr, which means that f is the vector field, we call that as a force field. So then you can evaluate the work that you have done, okay, along the curve. So that is a interpretation in terms of physical meaning of f dot dr. Only if your f is considered as a force field. But if you are given any other vector field, so you cannot just say that one is work done. Okay, only if you are given capital F here is the force field. Okay, for example, the example that I can show you, for example, this one. So the line integral, if you are given a force field and your force, you are given a vector field where your vector field here is a force field. So the f dot dr that you are evaluating, it is a work. You are computing a work that you have done along the curve C. Okay, so that is the interpretation of the line integral for vector field. Okay, now we want to evaluate. So how can you evaluate the line integral for vector field? Okay, before we proceed with the example, here I want to just a bit explanation the connection between the line integral of vector field and the line integral of scalar field. So what is the relation or connection between them? Okay, so again, now we start with the vector field. So the vector field is given by, in general, so this one in general, let's say you have a system in 3D, in space. So you have the function for component x, component y, and component z. So now how can you have f dot dr? So f is given. So dr is, what is dr? So dr here is coming from r in terms of t, where the component is x, y, and z. Okay, if you're given for component x, y, and z, so your dr should contain x, y, and z. But if you only have the I and j components, so you have only x and y. But in this case, you are given the in space, so dr, meaning that you have to differentiate, then you will give you dx, dy, dz. Okay, so f dot dr is p dot dx for component x, right? You know the dot product we have to multiply for each component, right? P dot dx plus q multiplied by dy, r multiplied by dz. So you have this one, p dx, q dy, r dz. Okay, if let's say your information r is in terms of t, so normally the vector function is in terms of t, right? So you have to, in order for you to solve this, because you have the x, y, and z all together, so more easier for us to convert them, all of them, x, y, z, into single parameter t. So you have to replace your dx in terms of t, your dy in terms of t, your dz in terms of t, and also your component of p, q, and r. So now, meaning that after you substitute everything, all the equation in terms of t, then finally you can evaluate the integral. So I don't want to explain in detail because this is very general. So we can see that in the example. Okay, so now you can see from the vector function where you have only f, now it reduces into scalar form, no more vector. So that's why here I just want to show you what is the connection between vector field and scalar field for line integral. Okay, so we start with the example. So example 1 for vector function.